you should now see notebook number 5. And I also increased the font size. I hope it's okay. If not, let me know. So we skip notebook 3 and 4 and continue with notebook number 5, which is the plasticity rule. So Christian already mentioned that we have two embedded general purpose processors, which we can use to alter the state of our network or of our neurons. So we have access to different observables, such as spike counters, correlation sensors, the membrane voltage, stuff like this. And we can use it to then formulate, for example, a plasticity rule to update the weights of our network. We again begin by some imports and defining a function where we will read an image. So basically we will read this image in and try to replicate this image by adjusting the weights of our network. So we will have, so this image is 64 by 64 pixels, and we will have 64 neurons, each neuron representing 1 pixel. And we will change the weights such that in the white parts, the firing rate is high. So there we have a high rate for the corresponding neurons in the row. And in the black part, we will have a 0 rate, so the neurons don't fire. And basically, we will have on the y-axis, we will have the different neuron numbers. And on the x-axis, we will have the time. So first, we read this image. We set up our hardware such that we can communicate with it. And now we define a plasticity rule. And we can do all this in Pine again. So this is more specific to our hardware. We have here a class, or we define a class, the plastic synapse, which inherits from the plasticity rule synapse and also from the static synapse. We will pass in a timer object. The timer object is also specific to brain scales. It defines when the plasticity rule will be run. So when it starts, for example, at 0, so it starts right at the beginning, and then for 64 microseconds or milliseconds, and how often or in what time intervals it will be run. We will also inject the image, which we loaded above, and also wait at which the synapses are configured at the beginning. So we begin by initializing our parent classes and saving the image in an instant variable. And also we assert that the number of periods in our timer object corresponds to our length of the image. In the next function, we define a so-called plasticity kernel, which will handle the weight updates during the operation. In here, we can write code for the plasticity unit. This is basic C++ code, which will then be compiled when you execute the experiment and be loaded on the PPU and will run at the specified at the times which you specified in the timer object. So what we do here, we define some variables. One's the PPU, so we have 2 PPUs, one at the top and one at the bottom of our chip. Next, we define a variable which will save the different pixels of our image. And also we will save at which row in our picture we are currently at. So we can update row after row and can construct our image. The entry for our plasticity unit will be the function plasticity rule kernel, which will be supplied with a set of synapses which belong to the population, and also with the plasticity unit. So if it's in the top half or in the bottom half, because you might want to have different updates rules depending on it. In our example, we will only use the PPU on the top part of our chip. So if this doesn't match, our PPU doesn't match to the top part, we just continue and don't execute anything. But if we are on the right PPU, we will update the different weights according to the pixel values in our image. So what we do, we iterate over the different rows in our synapse, or like over our different synapses, and then adjust the weights accordingly. So at first we iterate over the different rows. So you might still remember the image Christian showed at the beginning. So we have this synapse area, we have rows of different synapses and also columns. So at first we iterate over the rows and then define a weight vector for these synapses. And then later we iterate over the different columns, and then we test if the column is in our projection, and if so, we set the according weight to the pixel value in our image. When we have filled up our weight vector, we set all the synapses to the given weight. And at the end of our plasticity kernel rule, we increase the current row by 1. So in the next step, we will present the next column of our image. And here below, you see that we inject some information from Python, basically the height of the image, the width of the image, which was used here when we defined our image variable, and also we inject the different pixel values. So now I execute this cell, and we have defined our custom plasticity class. And the rest will look similar to the different the examples you saw before. So at the beginning, we call pine setup to start a new experiment description. This time, we will enable the so-called bypass mode. So we won't integrate the incoming spikes on the membrane, but just bypass the membrane and put them out. So each input spike will result in an output spike. Next, we define background input. We will use a spike source, Poisson spike source, which starts at the beginning of the experiment as a rate of 4 kilohertz. Again, you have to think about the speed up. So it will be about 4 hertz in biological terms or in real-time terms. And we will have a duration of 64 milliseconds, which corresponds that we present 1 pixel or 1 column of pixels every millisecond. Next, we define a population of 64 neurons, just our HX neuron, which you saw before, and we tell Pine that we want to record the spikes of them. The next step, we define the timer object I mentioned before. So we will start at the beginning of the experiment at 0 milliseconds, and then we'll run our plasticity rule every millisecond, and this 64 times the length of the image. Now we use the class we defined above to define a synapse. And this synapse we will use in our projection from the external input to the neurons. And here we have a one-to-one projection. So every neuron in our network has a single input neuron, which projects Poissonian spikes onto it. Now we can execute the experiment on the hardware. And it's now finished. And now we can plot the spikes of the different neurons over time. And we can now see that we recover the initial image from our input. So again, on the y-axis, we have the neuron index, and on the x-axis, we have the time. So this was a fairly short notebook. So if you have any questions, let me know, and maybe you can execute the code yourself in 1 or 2 minutes, and then I will continue with the next notebook. The next notebook is a bit more interactive. Now we will look at structured neurons. Before we looked at point neurons, so neurons which just have a membrane and have the same potential everywhere. But biological neurons, they have dendrite, axons, and they have a structure in general. So there are so-called multi-compartmental neuron models where you have different compartments which are isopotential themselves, and they are connected via resistors to each other. And with this, you can replicate biological neurons, the spatial extent of biological neurons. On our hardware, we realize it by connecting the point neuron circuits to each other, and which is displayed here in this picture. So we have the synapse area at the top, which you can just see here in the first box. Then we have two rows of neurons, top row and the bottom row. And here in the top row, I display the different connections we have between the neuron circuits. So we have one neuron circuit here on the left and one neuron circuit on the right. And for example, if you want to have this circuit as a compartment and the right circuit as a separate compartment, we could use these red connections to realize it. For example, we can disable the resistor here, use here a direct connection to the so-called shared line, close the connection in the shared line, and use a resistor here. So we will basically have two isopotential compartments connected by a resistor. And with this, we can create quite complicated neuron structures. In this example, in this notebook, we will show a simple chain of compartments, which is displayed here. So we have 4 compartments, and in between the compartments, the resistances. And below is displayed how we will configure it on the hardware. So we will use 2 neuron circuits to represent a single compartment. So the black boxes are neuron circuits, and the background color indicates what a compartment is. And then we will use the shared line to connect the different compartments. And for that, we can also use the Pine domain-specific language. Again, we set up our hardware at first, do some basic imports, load the nightly calibration, and then we begin defining our experiment. Once again, we start by calling Pine setup and providing a calibration. In the beginning, you can set some parameters of the network. The length is the number of compartments, which I choose to be 4, and the input is the number of synaptic inputs. So what we will do is we have this chain, and we will send synaptic inputs to one compartment after another and look how these postsynaptic potentials propagate along the chain. So if you want to have a higher input, you could increase this number, for example, to 15. And now we continue by constructing our chain. So we will define length times 2 number of neurons. So in the chain, each compartment is made up of 2 circuits. That's why we have the factor of 2 here. And then we will always connect 2 neuron circuits and later on add the connections between the different compartments. So at first, we define here the population of, in our case, 8 neuron circuits because we have a length of 4. And then we take a subset of this population, and for every second neuron, we connect the neuron to the right. So this is this connection here, this direct connection here, SMH. And we will also disable the leak conductance and also the capacitance. So basically, our neuron properties are given by the other neuron circuit in our compartment. Next, we establish the connections between the neuron compartments. So one compartment, we connect directly to the shared line, which I also showed before. And the other compartment we will connect via the resistor, and we also set the resistance, which is done via this value. And what we also have to do is close the connection in the shared line. So now we have defined our neuron circle or our chain of compartments. Next, we disable the spiking of the neurons so we can really look how the postsynaptic potentials propagate along the chain. What we also do, we define just helper compartments where we just look at a single neuron circuit, which will make it easier to later adjust for example, the conductance between the different compartments or to record the membrane traces. Next, we define an external input. So we set a time between the inputs. So at first, we input spike to the first compartment. Then after the interspike interval of 0.2 milliseconds, we inject an input to the second compartment and so on. So we create the spike train. And then in the next step, we create the projections between the input and the different compartments. So for each spike, we create an input population, which just has the size of the inputs we defined above, which I set to 15, and a single spike out of this spike times array. And then we connect this population to a compartment, to a single compartment. In the next cell, we define a function to set the conductance between the different compartments and also to record the membrane traces. So here at first, we have an input of the weight and also the conductance. So first we set the parameters. So here comes in the list we defined earlier. So we just set the multi-compartment Einweis and MDA, which corresponds to the conductance between the compartments to the defined value. And also we adjust the weight of the projection. Next, we will record the membrane traces. As Christian already mentioned in the first notebook, we use currently the high resolution ADC. That's why we have to perform the experiment several times. In our case, we have to perform it for each compartment separately because we want to record the membrane traces in each compartment. So we tell that we want to record voltage. We run our experiment. We again call pine reset to reset the time. And then we add the membrane traces to a list, which we will return at the end. The next code block is not so interesting. It's just a function that we can plot our membrane traces. And if you go at the bottom, you again can create a slider where you can adjust the weight and also the conductance between the compartments. And if you execute this, you will get the responses in the different compartments. So what we see here is the membrane voltage in values of the ADC, and on the x-axis is the time. And if we change, or like the first row represents if we inject an input to the first compartment, and the different columns represent where we record our response. So here we have an input to the first compartment and also record the first compartment. Here we have an input to the first compartment, but record the second compartment. And as you can see, as the signal propagates along the chain, it gets attenuated. And if we look at the second compartment, for example, now we see that the input or the PSP in the second compartment is the highest because this is the site where we inject our input, and it travels to both sides of the chain. We can see a slight asymmetry. So the PSP on the left side is higher because the left side is at the edge of our chain. So there can accumulate more current than on the right side, because on the right side it still has a neighboring compartment where some current flows to. So in the third compartment is basically the second compartment mirrored. and the fourth compartment the same as the first, but also mirrored. And now we can play around with our settings a little bit. For example, if we decrease the conductance between the different compartments, we will see that the attenuation is stronger. So after 2 compartments, we basically see no response, or just a slight response in our membrane trace. And also, I'm not sure if you looked at it, but you can look at the scale bar for the Y scale. Now it goes to 150, so we have quite a high response at the maximum. And if you increase the conductance, the attenuation will decrease. So we have a high response in later compartments, but also the response in the first compartments gets smaller because more current can flow away. We can also play around with the weight. So here we now have 100 approximately as the maximum. And if we increase it to almost a double, we will see that we almost double our response as well. So if you want to, you can play around a bit with the sliders, and you can ask further questions to this notebook or to any other notebook, or also questions in general.